Hi, Washington. So you have this calculus question, right? It says state the intervals of the function f of x is the square root of x squared minus 9 plus the square root of 16 minus x squared. You have to find where it's decreasing. So if we eyeball this thing, we can tell that there are two domain restrictions, right? So we can't square root a negative, right? So that says that x squared minus 9, right, has to be greater than or equal to 0, right? So we get x squared, we add 9 to both sides, is greater than or equal to 9. Now if I square root, right, square root of 9, that's 3, x is greater than equal to 3. Or if I take the negative square root, right, using rules of inequalities, the sign's going to switch. I put a negative here. Over here, right, 16 minus x squared has to be greater than or equal to 0. So I'm going to add x squared to both sides. Right, very similar to over here. Square root both sides, we get 4. So 4 is greater than or equal to x. Or, well, I should say, and negative 4 is less than or equal to x. So on a number line, so this is not the answer. This indicates the domain of the regular function. I am doing this because, right, we're going to have to take a derivative, right? You take a derivative to find intervals of increasing or decreasing. If it's not, if it doesn't exist within the interval, then it's not differentiable in the interval. So we're actually going to save ourselves time. So it's closed at -4, -3, +3, and +4. All right, so we have 5 intervals to play with. So if I were to plug in, say, -5, right? So -5 squared 25, 25 minus 9 is 16. It could work here, but -5 could not work here, right? So this interval is out. I'm going to come back to this. If I were to put in 0, right, 0 is a nice number, right? We get the square root of -9. So that cannot work. It could work here, but it can't work here. If I were to put in +5, that also could not work. So from the looks of it, right, if I pick a number in between 3 and 4, you can actually test this out if you want. I'm not going to do it for the sake of time. It's going to satisfy both conditions, right? So, like for instance, 3.5 for -3.5 is in this domain as well as the 16 minus x squared. So for the regular f of x, not f prime of x, I'm going to get to that in a minute. It's going to exist here, and it's going to exist here. All right, so now let's take a derivative. So we're gonna go to a new board. The square root of x squared minus 9 plus the square root of 16 minus x squared. So anytime we see radicals, I'm gonna put this in fractional exponent form. Right, that way we can use the power rule. So we have x squared minus 9. So this is f of x. So x squared minus 9 to the 1/2 plus quantity 16 minus x squared to the 1/2. All right, f prime of x. All right, so power rule followed by a chain rule. So that's going to be 1/2 quantity x squared minus 9. Centimeter to the negative 1/2. The derivative of the inside, the argument is going to be 2x. So let's see, times 2x. The 2 is going to cancel out with this 2, so I'm just going to be left with x. X in the numerator. And then this bottom portion, where this now negative fractional exponent is going to put this in the denominator on the bottom. So we get x, the square root of x squared minus 9. I'm going to put it back in radical form. So now I'm going to differentiate this. So it's going to be plus 1/2 quantity 16 minus x squared to the negative 1/2 times negative 2x. So again, this 2 cancels out with this 2. So we just have a negative x in the numerator, right? This negative x is this negative x over the square root 16 minus x squared. Extend this. Okay, let's get common denominators. So imagine if I were to put this radical 16 minus x squared here, I have to also put it up to this numerator. So you get x square root 16 minus x squared minus x square root of x squared minus 9, right? So I'm doing the same thing over here. So now remember, we set f prime of x equal to 0, right? To find mins and maxes. So I'm going to put equals 0, equals 0, and even this part down here. So this times that, well, actually, I'm just going to leave it as such. All right, set this to 0. So really, we're just looking in the numerator. We already know the restrictions in the denominator. So I could factor an x out. I'm just going to say numerator NUM. Then we're left with the square root of 16 minus x squared minus the square root of x squared minus 9 equals 0. Right, so right off the bat, this says that x is 0. But remember, it's not 0, right? Because it's not in the original function. So in this case, this is like extraneous. So I'm going to just say extraneous. So let's look here. So I'm going to go to add a new board. Get the square root of 16 minus x squared minus x squared, excuse me, minus the square root of x squared minus 9. Hmm. If I add this to this side, right, I could just square both sides to kill the radical. Add 9, we get 25. X squared plus x squared, that's 2x squared. Divide both sides by 2. So 25 over 2 is x squared. So x should be plus or minus. So if I square root this entire thing, the square root of 25, that's 5. Square root of 2 is just the square root of 2. Again, we don't like radicals in the denominator, so if I rationalize this, That's plus or minus 5 square root of 2 over 2. All right, so I'm gonna cheat a little bit. Well, not cheat. So I'm gonna use my calculator to see what this number comes out to be. This is an equal sign. If this number is in between -3 and -4 and or 3 and 4, then I can add this to the number line. So 5 square root of 2 divided by 2, 3.535 and -3.535. So it's in between it. So going back to the board, right here, I can add -5 root 2 over 2. Likewise, here I can add positive 5 square root of 2 over 2. All right, so we got everything we need. So, right, these are critical x values. The derivative, the first derivative is undefined at 3, -3, 4, and -4. In this case, right, which and all those numbers are here, which also happens to be key to the domain restrictions. And we have them on the number line. So if we use the first derivative test, right, we're going to test out 1, 2, 3, 4 different intervals. Right. So if I were to put a number between -4 and -5 square root of 2 over 2 into the first derivative, right, into this, and it comes out to be positive, then it's increased. If it comes out to be negative, then it's decreasing. Right, same thing for the second interval, the third interval, and the fourth interval. Okay, so I'm gonna grab the calculator, and I can check this with Desmos later. Hopefully you're familiar with Desmos, the graphing software. So -3, let's try -3.9. So what I'm gonna do, I add another word. So f prime of x, oh, where did that come from? So you got interval 1, 2, 3, and 4. Okay, so negative 3.9. Okay, so negative 3.9. So I'm using a calculator. Divided by the square root, negative 3.9 squared minus 9. Take that, subtract. Oh, I made a calculator error. Sorry, negative 3.9 divided by the square root. Of 3.9 squared minus 9 plus 3.9 divided by the square root 16 minus 3.9 squared. We get a positive number, right? So this area of interval 1, that comes out to be a positive number. So according to analytic, if you do the analytical method, this comes out to be increasing. So it's positive, right? So it's increasing. So according to patterns, right, this would probably be decreasing, but let's just do it for good measure, right? Especially consider that it's a critical point where we took the derivative. So if I were to put in, say, what was it, 5 root 2 over 2? Negative 3.2. So negative 3.2 divided by the square root of negative 3.2 squared minus 9 plus 3.2 divided by the square root 16 minus 3.2 squared. Now we get a negative number. So I was right. So interval 2 was negative. So it's decreasing. So actually I could call this number line f of x to f prime of x. This does not work all the time. It only works in this case because of how the numbers worked out with domain restrictions and things. Most of the time, you have to create another number line for f prime of x. So keep that in mind. Interval 3. So let's do 3.2. So 3.2 into here. So we get a positive number. So 3 is positive. So my guess is that 4 is going to be negative, right? So I think you get the idea, right? You just pick random numbers on a number line that falls into within the interval. So I would say that 4 is decreasing. So intervals 2 and 4. So 2 was negative 5 root 2 over 2, comma, negative 3. All right, we're going to use a union. 5 root 2 over 2, comma, 4. All right, let's check it on Desmos. I'm going to share my screen. All right, so the original function. All right, so you got x is the square root 16 minus x squared plus the square root x squared minus 9. All right, here we go. So it's decreasing, right? So again, negative 4, negative 3, 3, 4, right? That negative 3.536, that's negative 5 squared root of 2 over 2 if you write it as a decimal. Same thing here, right? So they're symmetrical. This is an even function. So it's decreasing here to here, right? So negative 5 square root of 2 over 2 comma negative 3. And it's decreasing 5 square root of 2 over 2 to 4. So that is how you handle those types of problems. I hope this helps. Let me know in the comments if anything's unclear, if I confuse you, you want more clarity or anything. Thanks.